This is a story about 2 different life histories. No, about 5. No, about 7. No, this is a story about how organisms approach carrying capacity and what they do when populations get there in terms of evolutionary responses. So for this lecture, I'd like you to be able to define and identify R and K life histories. Identify species along the R to K life history spectrum. And yes, it is a spectrum. Not everything is a dandelion or an oak tree. Define, as in a previous lecture as well, opportunistic, equilibrium, and periodic life history strategies. Now, I have already gone over those once in the lecture 24, but we're going to touch on them again briefly here. And this lecture topic is a little shorter. We're actually supposed to be doing in the in-person, we're doing catch-up before moving on to invasive species, because invasive species, it's going to be a little more activities and manuscripts. So yeah, this lecture topic is a bit shorter. I'm actually going to spend some time with you just going over some more examples if I can. So we're here at the population growth, logistical growth. So that's really what we're talking about for any of these species. And really, this is a lecture about carrying capacity. The logistical growth model incorporates certain resource limitations, and that's what's called carrying capacity. So how close is a population to carrying capacity is going to actually determine how well that population is going to grow. So we have this handy formula. And as you see, you have R max, the largest reproductive rate possible for an organism, so the most births, least deaths, times the number of organisms in that initial population. And that's going to be multiplied by this K minus N, which tells you how far the population is from carrying capacity, divided by carrying capacity. So the closer N is to K, the closer this amount gets to 0, which means the whole thing will get to 0. It's never a divide by 0 kind of deal. And if N is greater than K, then that's going to be a negative number. So all these things it's multiplied by are going to be negative as well. So carrying capacity is really that maximum population size. And when we covered the previous stuff about life histories, trade-offs, and these different opportunistic and periodic things, we always talked about, like, what are the things that are causing the death of the young? What are the things that are eliminating the fitness of the old? What are these things that are changing the population growth? And here's our logistical growth in some pictures. Here's that equation again. And what you may notice is some of these populations have an overshoot. So I want to kind of discuss that overshoot. And that is when N is greater than K. When N is greater than K, it's often a lag result of how many generations kind of have been in progress when the population actually reaches K. So think of it this way. You've got a large number of mountain goats, and those mountain goats are reproducing as rapidly as they can due to R max times N. What happens is they're going to be modified by K minus N divided by K, but that's modified after the population actually reaches that level. So if the mountain goats are pregnant and they're beginning to raise little mountain kids, then there will be more mountain kids plus the adult mountain goats than the carrying capacity can actually hold. And it'll be delayed by a generation. Or perhaps some of the old ones will still survive, even though technically they're grazing the resources down to the ground, and then they'll overshoot. And yes, I say grazing to the ground. That's because also K can change. So think about those examples when you had a drought and there was suddenly less vegetation. What happens? The animals eat all vegetation present. What happens when the drought goes away? Less things regrow. So K changes and organisms can overshoot. So in population dynamics time, you'll see a negative dn over dt, followed by a positive dn over dt as it rebounds. You can see that in the Daphnia here, followed by kind of an up and down, which will be slowly dampened to get closer and closer to actual K, until, of course, a storm comes or something. But there's often that overshoot. So that's in population time. what about in evolutionary time? How do organisms best get their life histories and life strategies to optimize their use of resources and their fitness? One way is R, having an R-based life strategy. And that's maximizing this R max, so the fastest possible R max. So what you have is the traits of this are pretty straightforward. You want to imagine an organism that wants to reproduce as fast as possible. And one of the rationales for this is it might be an organism that's reproducing in an environment that will go away, like a pond or something that will dry out. So development is very rapid. The reproductive rate is very high. The reproductive age is early. Body size is generally small. Length of life is short. Competitive ability, who needs to compete? Just make those seeds. Survivorship, high mortality of the young, yeah, because not all of them are going to be able to compete from a seed. Population size, there we go. It's variable. A single one of these dandelions lands, undergoes apomixis instead of real sexual reproduction, and produces 1,000 seeds. Okay, cool. 1,000 seeds go out. About 25% of them actually germinate and make anything useful of themselves. And then, I don't know, only half of those actually reach maturity. So now you have 125 dandelion babies. But remember, that's going to be in like a month or two. So you go from 1 to 126. They have that rapid development and young reproductive age that's happening in a few months. That parental care wasn't very high. They prefer this disturbed habitat because they have the open ground. Dispersal ability has to be good because, we'll get to it, you have those 126 dandelions, each of which can produce another 125. And you see within 2 generations, boom, the ground is covered in dandelions. Now they're competing with one another. They form this whole mat of dandelions here. And then something grows through the mat. Okay, let's say something is a maple, just some sort of silver maple tree. These are really nice trees, very competitive. And this silver maple tree grows above the mat of dandelions. It has no competition, except for water and nutrients for the dandelions, but it's a better competitor because our species are generally not that good at competitors. So it starts out-competing these dandelions, and after 2 or 3 years, it's shading out a large area. So within, you have a mat of dandelions, a few maples, and suddenly now you have a maple forest. And now these dandelions can't grow in that area. So they have, however, produced a lot of seeds that will have to move somewhere else because that area is all taken up with dandelions. So the dispersal ability has to be good to find new disturbed patches. And that's kind of your life histories for dandelions. Some other examples. So that live fast, die young. Think of mice. Think of cockroaches. Think of a lot of opportunistic bacteria that can grow in the human body when the human body is weakened. This is an R-selected strategy for growing very quickly, being able to develop very quickly. A lot of weeds are R-selected species. So cat's ear, lupin technically would be an R-selected species, but not as extreme as dandelion. You see, lupin takes 2 years before it can reproduce. Not like 5 weeks. I have something in my yard I call 6-leaf chickweed. It produces 6 leaves, and then it flowers and produces 100 seeds. It's impossible to weed it out because it only grows in about 2 or 3 weeks of spring, usually during finals. So 6-leaf chickweed is this perfect R-selected species. It also has a competitive ability of it's incompetent. It can't do anything. So it'll die out to grass, it'll die out to dandelions, it'll die out in your garden. Just crummy species. But out in my yard right now, it's rained recently, so all the seeds germinated. So I have probably 100,000 6-leaf chickweeds that are all trying to grow super fast. And if we have 3 or 4 weeks of warmth and sunny weather, then they would all go to seed. And that's the R-selected species strategy: is grow fast, make lots of babies. Then who cares? Death? Doesn't matter. Had seeds. On the other end of this spectrum that we're looking at, this is a spectrum, are K-selected species. And what we're looking for here is being able to reach that carrying capacity and stay there. So dominating the environment at carrying capacity. So let's look at a Gary oak. So I've planted one of these in my front yard, this Gary oak. The development is slow. Yeah, that chump's 3 years old. He's this tall. I mean, mine's going a little slow because the first year I had planted it, some little kid comes up and pulls it out. And like, I got your weed, Dr. Bodie. I didn't even call him Dr. Bodie. He's like, I got your weed, Sam's dad. And it's like, yeah, oh, come on. Put it back in. But it's tolerant. That's the thing. It has a strong competitive ability. It has a low mortality of young. These are good things. Reproductive rate is, well, low. This thing hasn't flowered yet. It's 3 years old, no flowers. Reproductive age is late. When it does actually reproduce, it's not going to produce a ton of seeds. The body size is large, yes. If this Gary oak grows to full size, it'll be about 1.5 meters in diameter of a trunk. And the size of the branches is really limited only by the amount of water available. It'll heave aside my driveway and shade out my lawn. It's huge. It will be huge. The body size is large. And it'll do that after about 100 years. The length of life is long. Now, oaks do die, but there's an oak down near Pigman's farm that I don't doubt is at least 200 years old, and it looks like it's got another 200, 300 years ready for it. Its competitive ability is very strong. So these are organisms that can dominate the canopy. And they do provide their offspring with these large acorns. So that's high parental care. They prefer habitats that are not disturbed, though. So if the plow were to come through, then this oak might die, and then in which case all its competitive ability counts for nothing. And it doesn't need to disperse a lot. It wants to develop K where it is, form a good population. If you go up to the intersection of Meridian and Highway? No, that has some good ones. Meridian and Ruddle? I can't remember. Oh, no. Martin and I'm completely forgetting the crossroad. But yeah, the end of Marvin. The end of Marvin, there's a ton of oak trees there. It's just this oak forest, and they do dominate this area. Sorry for spending so long trying to remember what road it is. My directions aren't what they used to be. It's near that bridge all those trucks knock themselves out on. Anyway, so that's the traits of this K selected species. Now some examples, of course, the oak tree. Douglas fir comes to mind, but if you wanted to go far into the K history, you'd go for Pacific yew, western red cedar, and western hemlock. These are organisms that will they'll dominate the forest canopy, and they'll dominate it pretty much until the forest fire, major windstorm, global flood, I don't know, whatever. They're going to dominate it for a while. Spruce can be this same way, especially out in the Hoh rainforest. Really K-selected, so they stay close to that maximum population size. So you note, though, I said not really Douglas fir. Well, Douglas fir isn't extremely K, like a Pacific yew would be, but it sure isn't a dandelion. It is a spectrum, and there are different places on that spectrum where these organisms will fall. Douglas fir makes a lot of young. It grows in disturbed habitats, and it grows fast, but it can live for 700 years. So it's got some R traits, and it has some K traits, and it's somewhere in there. If you had to ask me exactly where I'd put it, I'd say give me 10 other organisms, and I'll rank them. That's what it's really about. And we have other life history strategies, some other examples specific to plants. And what we're looking at is we've seen this periodic, opportunistic, and equilibrium species, but let's look at it in terms of stress and competition here. So first up would be your competitive plants. So for that would be, you think something like birch. Low disturbance, low stress, and that's where they'll dominate. So this would also be sugar maple is another good example of this. They're very competitive species. They're very shade tolerant, and they make a lot of shade. So they're really good for competition, but they don't dominate in times of stress. So stressful environments like a forest fire or even a grass fire will take out maple trees, will take out sugar maple trees. So they don't do well under high stress. On the other hand, you have the ones that do deal well with high stress, and that's going to be your stress tolerant. Yes, I was going to put it at C. The example here is beech, but you could also say the example would be oak as well. Oak is very drought tolerant. Oak is very wind tolerant. You can have a windstorm, you're probably not going to lose many oak branches. Oak is moderately fire tolerant. So there's a lot of stress it can take. Now, oak will be outshaded by the competitive maple in the absence of stress. But in the presence of stress and disturbance, the maples will go away. But what if there's a real lot of stress and disturbance? Well, that's where you're going to have rudderals. And rudderals are dominant when there's high disturbance and low stress. These are grasses that grow very fast. Because there's high disturbance, the ground is constantly tilled over, but they aren't very stress tolerant. Because grasses die, the grass withers and the flower fades, as they say in Isaiah 48. So that's going to be low intensity of stress, low intensity of competition, high intensity of disturbance. So there you have it. What about high stress, high disturbance? Well, that's sand. Plants don't do well under high stress, high disturbance. You're basically thinking of a place where the soil is constantly turned and constantly dry or burned, and nothing there. We discussed this a little earlier. I just kind of wanted to review it, the opportunistic, equilibrium, and periodic examples. I want to double check. Do I have another? No. Okay. So you're really looking at this in how much fecundity there is, how long the offspring survive, and let's see, I'm double checking how long the offspring survive, and when they're mature. So your periodic species are going to be the ones that have low juvenile survival, but high fecundity and late mortality. Your opportunistic is going to have low juvenile survival, low fecundity, and very early maturity. And I think I said high fecundity last time. It's actually relatively low. You just mature fast. And your equilibrium life history is going to have high juvenile survival, low fecundity, and late maturity. So yeah, those are the different types of strategies. Check with the last one. Check this graph. Cool. So how do species recover from disturbance? So this is a kind of an issue. So some species will actually welcome the disturbance. For example, grasses. Grasses welcome burning of the top. What they'll do is they'll grow all these upper leaves. And then when the sun hits and the water goes away, it's the drought time of summer, the leaves will just wither. And they leave all this withered leaf here. And it's a lot of matter that can be burned. Well, the apical meristem of the grass, the part that actually grows, is dormant and underground. So they welcome disturbance because it clears out all of that dead matter. Why did they make all that dead matter? Well, it also clears out the competition, allowing the grass to rise up like the phoenix in a brand new area. Then we have some types of pine trees actually will allow fire. Fire will come through the pine forest, and the seeds in the pine cones are actually safe and insulated, and they don't actually come out until they've reached a certain temperature, in which case the pine cones will pop out open and the seeds will be exposed to, after fire, hopefully, will be allowed to grow. So some species will recover that way. Others just have to recolonize. And when they recolonize, occasionally they'll recolonize fast, and they'll be exposed to some of the stressors of just no other plants around, which, no mulch, no small shaded areas. Some plants don't like that. Some plants love it. And when the plants that love it, they love that open area, they love the lack of mulch, they'll do very well. They grow right in after a fire. And others will have to come in under what's called succession, where they're going to have to outcompete the previously existing plants. All right, so for the next, we're doing a bit of an activity. We're going to cover 3 invasive plants discussed in class. I'm actually not sure how I'm going to roll this, but I know by the time I get to this, I will have already videoed it. Anyway, you'll be familiar with Solidago Altissimo, which is goldenrod. It's invasive in Europe. It's native in eastern North America. Cytisus scoparius, your Scotch broom, which is invasive in North America and is native in Europe. And Alaria petiolata, the garlic mustard, which is invasive in the Midwest and eastern parts of Europe, of America, but is native in Europe. So be familiar with these and think about as well, what kind of life histories do they have? Are they R? Are they K? Where would you put them on that list? I'll give you another clue. None of these are annuals. So what are they? R, K, somewhere in between? Classify them, and I will see you next time. Probably.